Good morning, everyone. So I'm Elke. I come from the Institut de Biologie Structurale in Grenoble, and I will talk about data processing and map calculation in time-resolved crystallography. So for those who've seen a presentation of me before, you might know that I like to explain things with Pac-Man, and that won't be any different during this presentation. So I always wanted to see how single protein Pac-Man works, and using time-resolved crystallography, I can now finally figure out how this structure, how single protein Pac-Man's intermediate structures look like. So the reaction that we want to look at is the following. So we have Pac-Man in its reference resting state, and when we trigger a reaction, he starts eating. And that's the structure that we want to probe with time-resolved crystallography, is the structure of our eating Pac-Man. So I go into the lab, I produce my protein, I crystallize, I optimize my microcrystals until I get nice batches of well-diffracting homogeneous microcrystals. These crystals I take to an X-ray source, so that can be a synchrotron or an X-file, depending on what you need. And I put the crystal in front of the X-ray beam to get diffraction images. Now, as you know, if we then apply a trigger just before the data collection, we can probe the structure at a certain time delay, delta t. Now, a very big difference with traditional crystallography, in which we rotate the crystal in the X-ray beam to probe all the orientations, is that in serial crystallography we only collect a single image for a crystal. And that means that we have to provide a stream of crystals in different orientations to capture all the different orientations. This means that one crystal leads to one diffraction image, and thus we have to collect many diffraction images to get a full data set. So typically during an experiment, I think most of you know, but nevertheless, let's make sure that everybody's on the same page. So we can collect data without applying the trigger, so that will give rise to our reference data set. So if you are collecting data on a light activatable protein, that will be your dark data set. Then we can also apply the trigger before data collection. That would be a light data set, but we most often don't collect in this way. We mostly collect in an interleaved fashion, so that might be light, dark, or light, dark, dark, and get different data sets. Good, so now that we have obtained our data, we can process the data. And again, because this is a very mixed audience, I want to give a little bit of basis of crystallography. So the main aim of data processing is basically to come from our diffraction images to just a list with the different reflections, their intensities, and their estimates of their error values. So from a diffraction image, we can find a reflection that we give an index HKL, and that is the Miller index, which basically defines its position on the diffraction image. And that's only dependent on the crystal lattice, and its properties depend on the symmetry. Then we can determine the intensity of this reflection, which is related to the structure factor amplitude. And the structure factor describes the scattered wave from the unit cell, so it's the Fourier transform of the electron density. But from the experiment, we can only extract the amplitude of the structure factor, so the phase is not measured. Nevertheless, it's very important because it defines the relative position of the unit cell content, but we can estimate these phases experimentally or via molecular replacement, in which we take the phases of another model to calculate our maps. So this is the aim. So we want to get a file with just reflections, their intensities, and their standard errors. The overall pipeline in data processing for serial crystallography is not so much different as for rotational crystallography, but there are some challenges, and I will discuss a few of them. But let's first go through a bit like how the pipeline looks like. So we typically start with an optional step, which is hit filtering, and that's to filter out empty images. Because in serial crystallography, we don't have that much control about whether we are hitting a crystal or not when we collect our diffraction images. So many of these images will be empty. Then we can do a peak search, so we want to define where the peaks are located on these images, and I think you can't even see on these images where the peaks are, but okay. Then we'll try to index the images. That means that we're going to try to annotate these Miller indexes HKL to each reflection, and thereby determine the crystal orientation, the unit cell, and the point group. Then, depending on the program that you use, there will be some parameter refinement or optimization. And then, of course, the very important step is that we integrate the reflections. Now, each reflection is measured multiple times, and so then we have to scale and merge all the reflections together into a data set that we then can use to solve the phase problem, calculate electron density maps, and refine our structure. So I'm mainly using the program Crystval, so this is mainly how this is done in Crystval, but other programs such as DALS, HCBX will follow a very similar scheme. Good. Some challenges that we face in serial crystallography. So there's several of them, so I just selected a few. First of all is that we need a very, very accurate geometry description. So we need to know at a precision of tens of micrometers the sample to detector distance, so the distance between the crystal and the detector. We also need to know exactly on the pixel where we find the beam center on our detector, and also the exact positions of the detector panels. And this can be rather challenging. So here on the right you can see two detectors which can be found at different X-file sources. So this is can be found at LCLS, this is a European X-file. And as you can see, these layouts are very, very different. And in addition, different panels can basically move between different experiments, which makes it very often difficult to get a good geometry description. However, this is really essential to index the most of our images. So just a little tip if you want to start data processing, you can start trying to make this a geometry description by just from scratch, but that's very hard. So you better ask your beamline staff for a geometry file. If you cannot obtain it in this way, you can check for deposited files from the same beamline, or you can ask software developers. They're mainly also up to date about which detector is used at which beamline. So good. Once we have a good geometry description, we can index a lot of images. But also there we face a specific challenge, and that is that we collect images from crystals with random orientations. This means that there exists no geometric relationship between subsequent diffraction images that we collect. And this is very differently, again, from the standard rotational crystallography, where you can clearly see that there is a relation between one image and its next image. So this means that each diffraction pattern needs to be indexed independently, and this can be very challenging, especially if you only have a few spots. So again, here, use dedicated software such as Crystval, DALS, HCBX. There might be others, and XDS, and so on. And these software will contain specific algorithms to index independent images. So good, we've indexed our images, and again, we find another problem, and that is that reflections are incompletely measured, and that's what we call partiality. So assume we have a reflection over here, and this would be the intensity profile once we would rotate the crystal in and out of the condition of diffraction. Now, again, in rotational crystallography, we this intensity profile will be probed by subsequent images. So the dashed lines that you can see here, that these show the start and the end of a new diffraction image. So that means from one crystal, we obtain a full intensity profile from subsequent images. In serial crystallography, this is not at all the case. So that means, like, for one crystal, we might probe just this part. From another crystal, we might probe this part. So this makes it very complicated to regenerate that full intensity profile. So there's different ways to deal with it. One is the most simple one. It's the Monte Carlo method, where the strategy is just like we collect a lot and then we average everything, and that will give us a good estimate of the average intensity. We can also go for some more complex schemes, and that's called post-refinement, where we try to assign and refine each the partiality and then scale each reflection as compared to the other. So we really try to model how each reflection is probed by the sphere. So these are different strategies. So while this is more complex, it might lead to much better results. However, if you have a lot of data, this might actually work very, very nice and give you very good results as well. So a last challenge I want to quickly touch on is indexing ambiguity. That means that crystals can be indexed in 2 or more orientations. So this means that 2 or more crystal orientations can lead to the same reflection positions. However, they're different reflections, and thus they will have a different intensity. So if we would merge those reflections together, we will end up with wrong estimates of the intensities. This can lead to apparent twinning and can make refinement very, very hard. So to illustrate what it actually means as indexing ambiguity, we're going to look at a little video of Mr. Bean. So this was an idea from Thomas White. So this is not my idea, but I find it absolutely great. So I hope we will not have any ads. So what we see here is we're going to start off in a little video at Mr. Bean at a dentist, and he just knocked down his dentist. So he decides to take care of himself. I don't know if you can sound. So what happened with Mr. Bean is that his mouth basically has no symmetry, right? Each tooth is independent of the other one. However, his X-ray image clearly has symmetry. So the image has a higher symmetry than the actual object. And this clearly leads to serious problems if not treated properly. So with that, we go back to the presentation. So for those of you who are interested to see the full video, it's Mr. Bean at the dentist. It's funny. Again, here, different software have different solutions to treat this indexing ambiguity. And so this is very important, especially if you do tests on your data and there's like signs of apparent twinning. Try to see if you have a space group which can have this issue. So good. So there's definitely many other challenges for serial crystallography data. But I think these are the ones which most people can face most oftenly. So luckily there's good software to deal with those challenges. And that means that if we have collected hundreds of thousands or even millions of images, we have indexed tens of thousands of them, we have collected or integrated our intensities, we have good data processing statistics, we finally have this list with the reflections and their intensity, which means that we can calculate and refine our structure. But when we refine this reference, the structure of this triggered state, what we end up is with the structure of our reference state. So what happened and how can we get this triggered state structure? Well, what happens is that you're dealing with a low occupancy of that triggered state. So that means that if we look again at our reaction, so we have the reference state, we apply the trigger to obtain the triggered state of our Pac-Man. So that means that if we crystallize Pac-Man in the reference state, we get this crystal, and crystallography is an ensemble-based method, which means that the average Pac-Man looks like this. So if you collect data on this crystal, the structure that we will refine is this one, which is the reference state. All fine. Now, when we apply the trigger in our crystal, what often happens is that only a few of the Pac-Mans reacted. So only a few of the proteins reacted, which means that the average Pac-Man is like this. And so when we refine the data, when we refine the structure in the data that comes from the experiment, it's most probably this and very far of the structure that we want. Now, luckily, again, there exists software that's dedicated to deal with this issue. Now, before we go into that, I also want to just introduce a real-life example, which is a fluorescent protein, of which we will show the maps later, and that will also be used this afternoon in the demonstration. So this is a fluorescent protein which has a chromophore in the center, and when you illuminate this protein, the chromophore undergoes an isomerization, and also several residues in its surrounding undergo conformational changes. But when you crystallize this protein and you illuminate the crystals and you collect data, you get a very nice electron density showing the reference state. So we are exactly in this case. So there exists different software. Some of the software will try to deal with the problem in reciprocal space. There's other software that try to deal with this issue in real space. But we're going to look very quickly how this is dealt with in Extrapolate, because I'm one of the developers of this software. But the other programs, they will work as well very, very good and help you with solving this issue. So to get the triggered state structure, what do we need? Well, we need, from our reference, we need a reference X-ray diffraction data. So the structure factor amplitudes for the reference. We also need the reference structural models. So that means that this phase information can be used to calculate the maps. And we need the triggered X-ray diffraction data. So that are the structure factor amplitudes from this experiment. And then we calculate a Bayesian-weighted Fourier difference electron density map, or in short, FOFO. In this, we just subtract one data set from the other, and we multiply by some weight factor to reduce uncertainty. So basically, we just subtract one data set from the other. And with that, we can calculate a difference map. You already have seen a few of them. So this shows an unbiased difference between the two states, because it does not assume anything about the triggered state, because we just use the data and the phases of our reference state. So what you see here in red is negative density, so these are features that disappear in our triggered state. And here in green we have positive density, so these are features that appear in the triggered state. So this is a very useful map, however, it does not allow us to refine the structure. So that's why we extrapolate the structure factor amplitudes, and with these structure factor amplitudes we try to mimic a situation in which the full crystal was occupied by the triggered state. And we do so by taking our weighted different structure factors from the previous slide. We multiply it by an extrapolation factor alpha, which is related to the occupancy, and then we add the reference state again. And these extrapolated structure factors, they can be, or extrapolate structure factor amplitudes, these can be used as normal structure factor amplitudes, so you can use them for reciprocal space refinement, and you can also use them to calculate maps. So what we see here on the left is the extrapolated map, which is the equivalent of a standard 2FOFC map. And here on the right, we have an extrapolated difference map, which is the equivalent of a standard FOFC map. But like instead of using the observations, we use the extrapolated structure factors amplitudes to calculate these maps. So with all of that, we did some data processing, some parameter optimization. We did some data reprocessing. Very often we reprocess quite a lot until we find the best spot of parameters. We refine the reference state. We calculate our Fourier difference map, our extrapolated structure factor amplitudes. And then finally, we refine our triggered state. So we're happy. We finally have the intermediate state structure we've dreaming up. And so since we're happy, I'm going to go to acknowledgements and stop talking in a minute. Because I first need to do my acknowledgement. So there's many people that have been involved in teaching me serial crystallography, but also have been involved in developing extrapolate. So in particular, I want to thank Jacques-Philippe Colletier, Nicolas Coquel, Thomas Barnes, all the extrapolate users, and very important software developers. So Extrapolate, for example, is built on CCBX, Phoenix, CCP4, and Qt. So this is very, very essential that these people are really acknowledged for all their work they do to give us this awesome crystallographic tools. And then, of course, also the people that develop the dedicated software for serial crystallography. So as I said before, I'm a Crystal user, so I'm very thankful to Thomas White to develop this software, but also other software developers of other tools are very important. And so this afternoon, I will give a very quick demonstration about how to process data in Crystfile and then calculate our maps and extrapolate. So see you this afternoon for the demonstration.
Thank you very much for this insight into problems from symmetry and other problems and how to solve them in particular. So we have time for questions.
Very nice talk, Elke. On slide 20, you had a note at the bottom about the extrapolation factor, and you had one divided by occupancy and two divided by occupancy. Could you elaborate more on that?
Yes. So there's actually some kind of so we use a simple reciprocal relationship, that this extrapolation factor equals one of the occupancy. But there's other groups that use that it divides like 2 over the occupancy, and this has to do with something that we typically see in difference maps. When your model is incomplete, then the difference map at that position will be shown at half the signal. Yeah, the signal will be only half of what you would expect if that feature was included in your model. So that's why we might need to multiply by 2. However, that's the same reason why in standard crystallography we calculate a 2FO minus FC map. So right now it's kind of unsure that if we do extrapolation like this and we calculate an equivalent of a 2FO FC map, do we need to apply this factor 2? And we also think that there might be other parameters which needs to be taken into account, such as the resolution at which you collected the data. As well, you can also see that we have this M and this D, so these are other weight factors that are typically used in crystallography. So what's the importance of them? So it's quite some work that we need to do, and it's definitely on our to-do list to really find the relationship to the extrapolation factor that we found and the real occupancy in the crystals. But with extrapolate, we report the occupancy as with this factor. But if you use if you have reasons to believe that there should be another relationship, you're of course free to use. But this is definitely on our to-do list to really dig into this much deeper, because it's important that we report the most probable occupancy. This is quite some work, though.